So much for the introduction. As Wade said, my name is Keith Gregorczyk. I'm an associate research scientist at the University of Maryland. And today I'm here representing our new startup company, Ionic Devices. And we're trying to do a pre-seed of 2 million. Slide. So we've all had a problem where your cell phone or laptop or your smartwatch fail because the battery expands, it breaks the case open. And an even worse scenario, the casing of the battery fails, the battery catches on fire and completely incinerates your device. And then if you advance the slide, please. And the absolute worst occasion this happens, the battery fails explosively in your pocket or on your body and causes severe lacerations, chemical and thermal burns. So our technology solves all these problems while also delivering simultaneous high energy and high power. Slide, please. So state-of-the-art lithium-ion batteries are currently made with 100-year-old techniques, which are pushed to their absolute limits. What we do is we adopt a semiconductor-based approach to make safe, solid batteries. And I'll give you more details on the process in a moment. The result of this is that batteries have simultaneous high energy and high power with a tunable cell voltage. Because we're using such advanced manufacturing techniques, we expect to produce about half the amount of CO2 for an equivalent amount of energy. And because the batteries are solid, they can operate at larger temperature windows, both hotter and colder. And finally, the method can produce batteries that have various shapes, so perfect for an already huge and rapidly developing electrical world. Slide, please. So like I said, lithium-ion batteries are currently made with very dated powder techniques that are based off of stuff developed during the Industrial Revolution. So these techniques cannot be scaled down, and they do not meet the volumetric needs of next generation consumer electronics devices. Furthermore, the liquid electrolyte used introduces safety issues as well as thermal management issues. So our technology is truly a revolution in manufacturing. We produce safe, solid batteries that leverage decades of semiconductor technology without the semiconductor price tag. So just like microelectronics industry, so if you look on the left there in slide A, we're using wafers. The only difference is our wafers are made of aluminum oxide and they have billions and billions of tiny holes in it. And we need the holes to be able to get enough material to get our energy density up. So then next in B, we pattern and process the wafer just like you would do if you're making memory or capacitors or resistors, etc. And so for this example, you can kind of imagine this grid, and inside each grid, inside each square of the grid, there's billions of 1 to 2 micron holes, and inside each one of those holes is a solid-state battery that we deposit there using very standard vapor phase deposition techniques. And then, so that gets us the high energy, and then the thin film gets us the high power. So next, we take that wafer, we cut it up into pieces, and so you can imagine each one of those little squares in the wafer is now an independent little battery. And at this point, they are all actual solid-state batteries. They just have a low energy density or low total amount of energy per die. And what we would do is then just stack the dies up inside of a packaging. This allows us to get to a total energy, also allows us to tune the voltage based on how we wire the internal dies, and it allows us to keep the volume quite low. Slide, please. So there's a little more detail, cross-section of what we're working with. And we plan to additionally leverage capacitor packaging that's routinely used in the semiconductor industry for things like multi-layer ceramic capacitors. So inside the package, we see cross sections of the die stacked up. So inside each of the billions of holes we see, you can see that there's a full solid-state battery with the cathode, the electrolyte, and the anode. And you can get a rough idea of the dimensions that we're using here. So the stacking in the middle there is how we get to whatever total amount of energy we want. And the more dies we put in the stack, the more total energy we get. And depending on how we wire them, which can be done pretty easily, and I don't show the technology here because we haven't patented it yet, but we can do this by using what are called internal MEMS pins. So there won't be an additional volume added by doing internal connections. Slide, please. So in terms of competitors, I have it here in 2 ways. First, I compare the state-of-the-art 18650 CAN cells. So these are the type of batteries you would see in like a Tesla. It looks like well, it's blurring out. It looks like a thick AA battery, and they sit at about 300 to 500 watt hours per liter. If you compare to a commercially available solid-state battery from a company like ST Micro, they sit at about 20 watt hours per liter. So at UMD, we're currently making batteries in 400 watt hours per liter, and we expect to be able to get to 800 watt hours per liter with Ionic Devices in the next 24 months. And we can definitely get higher than that by swapping out cathodes, but we can get into the details about that at the end. Slide, please. We've been working on this problem for 14 years, and there's been a total of about 30 million in non-dilutive federal investment. So the project originally began about in 2009, and it was just aimed at understanding the fundamentals between nanostructured materials and electrochemistry. And then now we are working on arrays of full solid state systems, and with your guys' help, we're going to commercialize all this. Slide, please. So we've done some initial consumer discovery through the NIA program. And the area we've landed on is consumer electronics, but particularly the Internet of Things, or IoT. So just to define that, IoT is generally non-standard computing devices. They connect wirelessly to a network, and they have the ability to receive and transmit data. So on the industrial side, you can basically think of distributed sensor arrays for applications like monitoring green energy production, in traffic spaces to keep track of bridge stability, road conditions, things like that. In the manufacturing space, you can imagine having sensors on large inventory spaces and being able to rapidly know what you have and where it is. And then in agriculture, it's very, very similar, where you can measure nutrients and moisture levels, for example, in a field, or know your tractor in principle could be an IoT device, because you could check on your phone what the fuel levels are. And then on the consumer side, this is stuff we work with or have around us more often. This is in many sense your cell phone, your smartwatches, your Fitbits, everything that you're wearing or is in your house, and it's keeping track of things you do. And so we've begun talking with all these companies like Whoop and Medtronic, Wiliot, Boston Scientific. We had a great conversation with Garmin about a week ago, and we're meeting with Black & Decker soon. Slide, please. So all that data we've sort of coalesced into this opportunity attractiveness map, and so you can see here that we plan to go for the consumer industrial IoT space. This is about an $8.5 billion industry currently, and it's expected to grow about 17% by 2030. So a large space of growth there still. It's important to note that we would also be quite disruptive in implantable medical devices. However, these devices require up to 7 years of approval by the FDA, so it's not really a great space for a startup company to pursue. But everything we learn in the industrial and commercial IoT space will be automatically applicable to them, and I think we would have some traction in a few years in that space as well. Slide, please. So our business model is largely based on the way batteries are currently distributed. And the way that works now is that the batteries are sold to a distributor, and then the manufacturer will request them from the distributor to meet a customer's demand. So the way we would have to approach that is to talk to end customers to get the desired specs that they want, and then try to help get some pull from them through the distributors. Though I think it's important to note that with the Biden administration's push to reshore manufacturing and supply chains, this might change, and we might actually have a direct route from us to an end consumer who's some electronics manufacturing corporation. Slide, please. So we're asking $2 million in pre-seed, and we've tried to break the phases up to best deal with the risk associated with developing a new manufacturing process. So the pre-seed phase, we address the manufacturing risk by contracting with foundries to do the initial sample fabrication. We already have a good working and personal relationship with both Forge Nano and Vigo ALD, and the companies are both quite excited to work with us. This is a dual advantage of quickly producing a set of samples to validate the manufacturing process, while also allowing us to evaluate the equipment that we eventually want to buy or start buying in phase 2. And then once we do that in phase 2, the goal is to try to get to test kits so that we can get them into customer hands. And phase 3 would be raising a Series A off the test kits. Slide, please. We have a great team lined up to do this. Myself, I'm an associate research scientist at the University of Maryland. Like I said, my expertise lies in the intersections of solid-state electrochemistry, energy storage, and semiconductor manufacturing. We have Joel Blanco, who's on the call right now. He's currently working at Intel, and he's our business advisor. Dr. Nam Kim has been leading the sample production at UMD, and then Professors Gary and Sangbak Lee have been working on these on this problems for 20 and 30 years or 50 years combined, depending on how you want to look at it, and are essential to the scientific background and success of the company. Slide, please. So thank you so much for your time and for this opportunity. I really appreciate it. And if you have any questions, I'm happy to answer them. And I leave you with a more detailed Burgon plot if anyone knows what that is and wants to talk about it. Questions?